For most of human history, the search for life beyond Earth was a matter of imagination. We had no way to actually look. We could speculate, write stories, build entire mythologies around the possibility of other worlds, but we had no instrument capable of testing those ideas against reality. The question of whether we are alone in the universe was philosophical. It belonged to poets and theologians as much as to scientists. That changed completely in the last 2 decades. We now know of thousands of planets orbiting other stars. We have catalogued worlds that are rocky, worlds that are gaseous, worlds in the so-called habitable zone, where liquid water could theoretically exist on the surface. For the first time in history, the search for alien life stopped being purely philosophical and became an actual scientific program, with actual targets, actual data, and actual instruments capable of gathering it. James Webb was supposed to be the turning point, the moment when we finally got close enough, with instruments sensitive enough, to start answering the question seriously, to look at the atmospheres of these distant worlds and search for the chemical signatures of biology, oxygen, methane, the telltale combinations of gases that, on Earth, exist only because life produces them. And Webb has been looking. For the past several years, it has been turning its instruments towards some of the most promising candidates we know of rocky planets in the habitable zones of nearby stars, worlds that, on paper, looked like they had everything required for life. What it found is not what anyone hoped for, and the truth it's revealing about the nature of alien worlds is harsher and more sobering than most people are willing to admit. Let's start with the planets that generated the most excitement in the first place, the TRAPPIST-1 system. TRAPPIST-1 is a small, cool, red dwarf star located about 40 light-years from Earth. What makes it remarkable is that it hosts 7 rocky planets, several of which sit in what astronomers call the habitable zone, the region around a star where temperatures could allow liquid water to exist on a planet's surface. When this system was discovered in 2017, it was treated as one of the most promising places in the galaxy to search for life beyond our solar system. 7 rocky worlds, multiple candidates in the habitable zone, a relatively nearby star. It seemed almost too good to be true. James Webb has spent significant observation time studying these planets, attempting to characterize their atmospheres using a technique called transmission spectroscopy, analyzing the light from the host star as it passes through a planet's atmosphere during a transit, looking for the absorption signatures of specific molecules. The results, published across several papers between 2023 and 2025, have been consistently disappointing. TRAPPIST-1b, the innermost planet, shows no evidence of a substantial atmosphere at all. TRAPPIST-1c, initially considered one of the more interesting candidates, also appears to lack a thick atmosphere, with some models suggesting it may have a thin carbon dioxide envelope at best, more similar to a scorched version of Venus than to Earth. The data for TRAPPIST-1d, e, and f, the planets most squarely within the habitable zone, has been frustratingly inconclusive, partly because their atmospheres, if they exist, appear to be thin enough that Webb's current instruments struggle to characterize them definitively. But here is the most important finding, and the one that has shifted how scientists think about red dwarf systems in general. Red dwarf stars, even quiet ones, produce flares and high-energy radiation that may be devastating to planetary atmospheres over long timescales. TRAPPIST-1, despite appearing relatively calm compared to other red dwarfs, still bathes its planets in stellar wind and high-energy particles, intensely enough that current models suggest the inner planets may have lost most of their original atmospheres over the system's multi-billion-year history. The harsh truth emerging from this research is that being in the habitable zone is not enough. A planet can have exactly the right temperature for liquid water and still be uninhabitable, because the star itself is hostile in ways that have nothing to do with distance and everything to do with the violent, high-energy environment that small, cool, magnetically active stars create. The second harsh truth comes from a planet that generated one of the most significant controversies in recent astronomical history, K218b. K218b is a planet, roughly 8.6 times the mass of Earth, orbiting a red dwarf star about 124 light-years away. In September 2023, a team using Webb's data announced the detection of dimethyl sulfide in the planet's atmosphere, a molecule that, on Earth, is produced almost exclusively by biological processes, primarily marine phytoplankton. The announcement was treated, understandably, as one of the most exciting potential biosignature detections ever made. The excitement was, in retrospect, premature. Subsequent analysis by independent research groups raised serious questions about the detection. The statistical significance of the dimethyl sulfide signal was lower than initially reported. Some groups, reanalyzing the same data with different methodologies, found no clear evidence of the molecule at all. Others suggested that the spectral features attributed to dimethyl sulfide could be explained by other, non-biological molecules with overlapping absorption signatures. By 2025, the consensus among atmospheric scientists studying K218b had shifted considerably. The planet, rather than being a potential ocean world with biological activity, is now thought by many researchers to be what's called a sub-Neptune, a planet too large and with too thick a hydrogen-rich atmosphere to have a habitable surface in any conventional sense. The pressure and temperature conditions beneath such a thick atmosphere would likely be incompatible with the kind of liquid water surface that was initially envisioned. This case illustrates something important about the current state of exoplanet biosignature research. Our instruments are operating at the very edge of their capabilities. The signals we're trying to detect are faint, the atmospheres we're trying to characterize are often poorly understood, and the line between exciting potential biosignature and statistical noise interpreted too optimistically is thinner than the public discourse around these discoveries often suggests. The harsh truth is that we have, on multiple occasions now, gotten excited about signals that didn't hold up to scrutiny. This is not a failure of the science, it's how science is supposed to work, with claims tested rigorously before being accepted. But it means that the path to confirming life on another world is going to be much slower, much more contested, and much more frustrating than popular expectations suggest. The third harsh truth is perhaps the most fundamental, and it concerns the planets we once considered our best hope, rocky worlds around the most common type of star in the galaxy. Red dwarfs make up roughly 70% of all stars in the Milky Way. Because they are so common, and because their habitable zones are close to the star, making transiting planets easier to detect, a huge fraction of the potentially habitable planets we've discovered orbit these small, cool, long-lived stars. But Webb's observations, combined with theoretical work on stellar physics, are painting an increasingly difficult picture for life on planets around red dwarfs. The habitable zone of a red dwarf is close to the star, often closer than Mercury is to our Sunday. This proximity means planets in the habitable zone are subjected to intense stellar wind, frequent and powerful flares, and high levels of ultraviolet and X-ray radiation, especially during the star's youth, when red dwarfs are significantly more active than they become later in life. This early period of intense activity can last for hundreds of millions to over 1 billion years, enough time to strip a planet's atmosphere before life has any meaningful chance to establish itself, let alone evolve into anything complex. Additionally, planets in the habitable zones of red dwarfs are very likely to be tidally locked, meaning one side permanently faces the star, while the other remains in permanent darkness. This creates extreme temperature differences between the day side and night side, potentially causing atmospheric gases to freeze out on the dark side, depending on atmospheric circulation patterns and composition. Webb's atmospheric studies of several tidally locked exoplanets around red dwarfs have found atmospheres that are thin, depleted, or in some cases, apparently absent altogether, consistent with the kind of long-term atmospheric stripping that the stellar activity models predict. This is the harsh truth that's reshaping the field. The most common type of star in the galaxy, hosting the most common type of potentially habitable planet we can detect, may be among the worst possible environments for the long-term development of life. The statistics of exoplanet discovery have been telling us we live in a galaxy full of habitable worlds. The physics of stellar activity is telling us that most of those worlds may be sterilized before life gets a meaningful chance. There is a deeper pattern emerging from all of these individual findings, and it's worth stating clearly because it changes how we should think about the search for life going forward. Habitability is not a single property that a planet either has or doesn't have. It is the product of an extraordinarily delicate balance between many factors: the type of star, its activity level and history, the planet's distance and orbital characteristics, its mass and composition, the presence or absence of a strong magnetic field, the history of impacts it has experienced, the composition of its atmosphere, and the geological processes operating beneath its surface. For decades, the search for life focused heavily on one variable: distance from the star, defined narrowly in terms of temperature. The habitable zone, as originally conceived, was simply the region where a planet's surface temperature would allow liquid water. This was a reasonable starting point, given the limited data available. But Webb's observations are revealing, with increasing clarity, that this single variable massively oversimplifies what's actually required. A planet can be at the perfect distance from its star and still be uninhabitable because the star is too violent. It can have the right temperature and still lack a viable atmosphere because of insufficient gravity, the absence of a protective magnetic field, or a violent history of stellar wind stripping. It can have liquid water and still be incompatible with the kind of complex chemistry life requires because of toxic atmospheric composition or extreme pressure conditions. The number of factors that all have to align simultaneously, and for sustained periods measured in hundreds of millions to billions of years, is larger than the early optimistic models of habitability accounted for. And as Webb characterizes more and more of these worlds in detail, the fraction of planets that satisfy all of these conditions appears to be shrinking, not growing. I want to be clear that none of this means the search for life is over, or that it's hopeless. It means something more nuanced and, in some ways, more interesting. Webb is still in the relatively early stages of its exoplanet characterization mission. The planets it has studied in detail so far represent a small fraction of the thousands of known exoplanets, and an even smaller fraction of the planets that likely exist in our galaxy. The targets studied so far were chosen partly because they were observationally convenient, close enough, with favorable transit geometry, orbiting bright enough stars to make detailed spectroscopy feasible. They are not necessarily representative of the full diversity of planets out there. There are upcoming missions, the European Space Agency's Plato mission, NASA's planned Habitable Worlds Observatory, specifically designed to expand this search considerably, targeting sun-like stars rather than red dwarfs, and aiming to characterize planets that may offer more favorable conditions than the systems Webb has focused on so far. But the harsh truth Webb has revealed needs to be absorbed honestly, because it recalibrates our expectations in an important way. The galaxy is not simply full of Earth-like worlds waiting to be confirmed as habitable. The path to finding genuine evidence of life elsewhere is going to be longer, more difficult, and require more painstaking, skeptical, rigorously tested observations than the early excitement around exoplanet discovery suggested. This is not a reason for despair. And it is a reason for patience and for a more sophisticated understanding of just how special the conditions that produced life on Earth actually were. There's a way of thinking about this that I find genuinely useful, and it comes from flipping the question around. Instead of asking, why haven't we found life yet, it may be more productive to ask, what would it actually take? And the answer that's emerging from Webb's data is humbling. It would take a star with the right balance of stability and energy output, not too violent, not too dim. It would take a planet at precisely the right distance, with precisely the right mass to retain an atmosphere and generate a protective magnetic field. It would take a multi-billion-year history without a planet-sterilizing catastrophe. It would take a starting chemistry capable of producing the kind of complex molecules that can self-replicate and evolve. Earth had all of these things, not because it was destined to, but because of a specific, contingent sequence of circumstances that, as far as we currently know, has not been definitively confirmed to exist anywhere else. That is the harsh truth Webb is revealing, observation by observation, system by system. Not that life doesn't exist elsewhere, we genuinely don't know that, and the universe is vast enough that confident claims in either direction would be premature, but that the conditions required for life, and especially for the kind of complex life capable of asking these questions, may be far rarer than the optimistic exoplanet statistics initially suggested. We are not finding a galaxy teeming with habitable worlds. We are finding a galaxy of extraordinary diversity, where most of the doors that look promising are, on closer inspection, closed. And in that difficult, sobering picture, the conditions that produce life here on Earth look less like a common cosmic occurrence and more like something extraordinarily rare. We are still looking. The search continues, with better instruments and better targets ahead. But the truth Webb has revealed so far asks us to hold our hope with more patience and more humility than we did before we had the data.